So we're going to look at the second part of the lecture, which is the database environment. So we are going to move to understanding a little bit about some aspects of the DBMS. We're looking at the theoretical and practical ideas concerned with the structure of databases and database management systems. And throughout this lecture, what I hope you will do is learn to define and discuss the ANSYS Spark architecture, which is a proposed architecture for a DBMS that will ensure these ideas of independence of data, and then look at the major components of a DBMS and be able to explain them. Note that any of those things could be questions in the exam, of course, so you need to be able to do it. And if you come in late, make sure that you sign, because I've put another signing thing around to see who is here for the long haul, as opposed to just for the first part of the lecture, which does not count in my books. So we have to then, for this part of the lecture, read chapter 2 and chapter 3 of the book. This is your reading, so at the end of this session, you really need to go away and read 3 chapters of the book in order to begin by being in tune with the subject. And what we're going to look at in this second part of the lecture is what we call the ANSYS Spark 1975 architecture. And the reason why we want to look at that is not necessarily an architecture that might be implemented in every database management system. It's not the standard, but it does allow us to understand quite well the functionality of the DBMS, and also this idea of how we can achieve this data independence, which is important as a concept in databases. It will actually allow us also to define some commonly used terminology, and it will give us this idea of the implementation, which is independent of the other layers of representation of the data. So it is a 3-level architecture, which should give it away. It has 3 levels in it. There is an external level, there is a conceptual level, and there is an internal level. Now, the external level is how the users perceive the data. And there might be more than one view to support different groups of users. The conceptual level is how the database management system and the operating system perceive the data. So this is the global definition of the data. And the internal level is how the data is actually stored in data structures. So we are separating by having this 3-level architecture, the implementation details from the data definition, from how the users perceive the data. And that is the important thing to do. So why do we want to have that? All of the users can access the same data, but each of them needs to have their own view of the database. So we want to support different users' views of the data from the one conceptual database. So this is the first thing that we want to do. Also, the users do not need to concern themselves with the physical aspects of data storage. Because we want to have this level of independence, we want the users to use the data without having to worry of where is it physically stored, how is it physically stored, or any of the access problems. So we're providing this independence by separating the data in this way. So the DBA, the database administrator, might make changes to the storage structure without affecting the users that are using the data. And the internal structure is going to also be unaffected by the changes that we make to the physical aspects of storage. So all of those things are the kind of things that we're trying to achieve. So we have something like this. We have an architecture in which we have an external level, and that in this case has 3 different views for 3 different sets of users. There might be more than 3. We have a conceptual level at which we define the whole entire database for the whole entire organization, and from that we derive the user views. And we also have an internal level, which is defined by the internal schema, and that is looking at how do we store the data. So we separate the functionality, we separate the data in that way, and then the internal schema then accesses the data in the database. And there is where we have the details of the physical organization. So when we look at the external level, well, we're looking at the user's view of the data, or a number of users might have the different views of the data, and they're going to be users that might be application programs that are written to access the data and manipulated in particular ways. There might be ad hoc users who want to fire specific queries to the database and get an answer. There might be, what they are going to be doing is accessing a specific part of the database, but they're all accessing the same conceptual database. So there is one definition of the data. And from that, we have different views. And each view might apply different naming conventions. So one field might see the student name as a student name. Another user might see it as a surname and first name and title. So you can provide each view to each user, which can be customized to their needs. So from the same data, I can derive different customizations of the data. So at the conceptual level, which is the middle level, we have the community view of the database. And this is a definition of the entire database upon which the external views rely. It has a logical description of the whole database as seen by the database administrator. It has entities, attributes, and relationships, which is how we describe the data in the relational model. And we're also going to have in there the constraints and integrity rules to support the internal view. So in any data, there will be constraints about how we use the data. A student might only be allowed to enroll in 120 credits a year. So that is a constraint in the data. I have to store that somewhere. So that is going to be stored in the conceptual level. I might also have security rules. A student is only able to access his own marks. So that is a security rule which needs to be stored at that level. There's only going to be one of these descriptions, one conceptual description of the data, where there might be many user-level descriptions of the data. So this one description is going to support all of the external views that the users are going to be accessed. And at the same time, it is not going to have any storage-dependent details. So we are removing the implementation aspects from this view of the data. We're not concerning ourselves at this stage with the implementation aspects. We're only concerning ourselves with the data that we need to provide the users their view of the world. At the internal level, which is the lower level, is where we get into the implementation details. So here is where we begin to look at the physical representation of data on the computer, and how we are going to implement all of the data access to make the access efficient. So we will be looking at things like indexes, if we have the data encrypted in particular ways, where we're going to access the data, etc. So storage devices, storage structures, indexes, compression, encryption are all going to be part of this internal level. So in a real scenario, you might translate it to something like that. Let's say that in our conceptual level, what we have defined is a staff entity which has a staff number, first name, last name, date of birth, salary, and branch number. From that, I derive different external views. One external view might require the staff number, but we're calling it differently for this group of users. It's called S number. And first name and last name, and instead of the date of birth, what I'm going to present with this age of users is the age, which is derived from the date of birth, and the salary. Whereas another view of the same data, another set of users, might see the staff number and call it a staff number, and the last name and the branch number. So each user has his own view, and it can be customized to their own requirements. And then that conceptual level is supported underneath by the definition on the internal level. So this is where we're specifying this might be some form of a record, extract the stuff, and the different kind of like fields that make this record, and the fact that it's some kind of pointer to the next stuff, so maybe it's implemented as a linked list. But these are all implementation details which appear at the lower level. So the higher levels don't have to be concerned with this implementation detail. And we also know that there is an index on staff number and an index on branch number. So that's where we are defining that kind of detail. What we have in there is we have said there is an internal schema and a conceptual schema and external schemas. So when we talk about a schema, what we're talking about is a description of the database at a particular level. So the description then becomes the schema. And there are schemas at each architectural level. You have the external schemas, which are more than one, which can also be called sub-schemas. You have conceptual schema, and you have the internal schema. All of those are defined. There is one conceptual schema and one internal schema, but there might be many external schemas. And what we have, what the database management system has to do, is to provide a mapping between one level and the other level. So it needs to know how to map from the conceptual level to any of the external levels. It also needs to know how to map from the conceptual level to the internal level to find out where the data is stored and how it's stored, etc. So the database management system is going to be providing the mapping between the different levels at which we define the data. And that is where we therefore can have this data independence, which is quite an important concept to us to be able to put through this database model. So what we want to have is this as an objective, and therefore we can implement it now in two levels. We can have what we call the logical independence, which is going to be an immunity of the external schemas to be affected by changes in the conceptual schema. So I can change my conceptual schema, I can add new fields, I can add new files, I can add whatever I want, I can change it, and I will not affect all of the external schemas that are derived from it. I might affect some, so if I change a particular field, one of the external schemas uses it, I might have to have some changes that are related to that, but that would be an isolated thing that is affected, not the whole entire different external views, etc. So I am trying to isolate that when I make a change to the conceptual schema, it doesn't affect all of the external schemas. On the other hand, I also have this physical data independence, and this is the immunity of the conceptual schema to changes in the internal schema. So then again, I can go and decide I'm going to have a new index, I'm going to change where I store the data, I'm going to change the structure of the record, and that is not going to affect the conceptual schema, and it might not necessarily affect the external schemas. So I'm trying to implement this independence where I can actually change the data without affecting the other levels. And that is the important thing to understand in this. So to define the schemas, I use my data definition language, which we have talked about before. It allows me to define objects in the database and the metadata. So I need a data description language or data definition language, and with that I can specify the database schema. And I can create the metadata, the data that is associated with the data that explains what data I am storing, what types, what constraints there are on it, etc. And that is going to be stored in what we call the system catalog. Every database management system is going to have a user-accessible system catalog which stores the metadata, or the data about the data. And that is the result of compiling the data definition language statements to make up the objects in the database. Sometimes you will also hear of something like the intention of the database or the extension of the database. The intention will be the definition of the data, the database schema. The extension will be the database at one particular time with one set of records, let's say one set of students. It will be how that is physically realized with a set of any particular instance of the database, set of students or a set of staff records, etc. So how are we going to design these schemas that we need to design in order to design a database? We need to produce a model of the data of interest, which is sometimes called the universe of this course. So I have to look at the enterprise I'm trying to model, and I look at what data is of interest, what objects are of interest, and I try to produce a model of that, generally using things like entity relationship diagram techniques. So the data modeling process is the process of providing this high-level description of the schema. And the data model, in that concept, is going to be the collection of concepts that describe the real world entity that I'm trying to model, and how I am going to manipulate that data, and the relationships between the objects in the data, and the constraints of the data. So all of those things are going to be part of the data model that I have to decide. There is a number of data models that we can use. You have things like object-based models, and within that we have, for example, entity relationship model. We will study that as part of this course. We are going to look at ER diagrams and how we create ER diagrams. They are one of the main techniques for database design. You can also have object-oriented models, and they extend onto the state of the object as well as the description of the object. We're not going to look at those in this course. We can also have record-based models, and as part of that we have the relational model. Again, this is part of what we are going to study, and we will see how we translate an entity relationship model into a model in the relational model world. And there are also other models, like the hierarchical and the network model, the ones that we talked about earlier, which relied on knowing the structure, etc. We will not study those because they are older models, but they exist. The models are translated into a data definition language for a given DBMS. We're going to be using Postgres, so we will use SQL, and we will define our objects into the data definition language SQL, but for Postgres, so we will then be able to create those objects in a Postgres database. So once we have done the definition of the data, we are going to want to manipulate the data. So then we go to the data manipulation language. We need to begin to understand how we are going to manipulate data. So we might want to query the data, insert, update, delete, and all of those things we can do through interactive SQL. We type an SQL query, the system brings back the reply. So that is interactive. We can also interact with the database by an applications program. So we write an application in Java, and with that we embed SQL statements and we access the data through the application. So that is a different way of accessing the data. We're still going to use SQL, but in this instance we're going to use it through an applications program. So we will study that as well. In particular, we're going to study that through the use of Java and JDBC. But that is not the only way that we can do it. There are also things like C++ and Visual Basic. They will use things like ODBC, OLEDB, ADO. All of those things can also be used, but we are going to concentrate on JDBC. And we can also access a database through web pages, but again, this is something that this course is not going to cover. We're going to concentrate on just the JDBC Java. There are also access possible through fourth generation languages, and these might be things like forms that you might find in packages like Access or report generators, etc., that allow you to do rapid application development. We're not going to look at those, but they exist in there. And there are ways of manipulating the data. So having looked at all of that, we just need to look at the components of the database management system. Now, I said to you that a database management system in the earlier lecture has to provide a number of functions. And remember that all of the access to the data is now going to happen via the DBMS. So there is no access to the data outside the database management system. So from that point of view, the database management system has to provide a series of functions or services. And these are things like safety and concurrency and security and recovery and integrity of the data. All of those services that we talked about have to be provided by the DBMS. So this is a possible architecture, not necessarily the only architecture that you're going to find, but example architecture of the database management system. So you are going to, and sometimes this might be one of the things that I could ask in an exam, could be, give me a potential architecture for a database management system, in which case you could come up with a diagram like this and an explanation of the components. So this is the kind of thing that I will be looking for. So we have programmers which are interacting with the database via applications programs. We have users which are interacting with the database via queries. And we also possibly have the database administrator who is interacting with the database, looking at the database schema, making changes to it, etc. All of those accesses go via the DBMS to the database. Now, the database management system is going to request access to the data, but it will be the file manager via access methods that are set up in the operating system and access to the system buffers that will manage the access to the data. But all of this access is going to be controlled by the DBMS. So it has to perform a series of functions. If it gets data manipulation language statements, it has to preprocess them and compile them, and from that we get the queries that the DBMS is going to run. Now, they might be put through the query processor because there are many ways to implement a particular query. Some of them are going to be more efficient than others. So the DBMS has to decide how to execute a particular query in an efficient way, so the user doesn't have to wait a long time for the response. And the same query could be executed in a number of ways. This is quite a complex area to optimize queries. So there is this idea of the query optimizer, the query processor, which is going to manage the queries. Any data definition language will go through a compiler, and the results of that will interact with the dictionary manager or the catalog manager, which will contain the metadata. And all of those things are going to interact with the database manager. Now, in the next page, we're going to see that the database manager has to do a whole lot of work to comply with a particular request, because this is the component that does the majority of work in the database management system. So when we look at that, and we have as before the program object code, the query processor, and the catalog manager, all of them, giving queries for access to the data, changes to the data, etc. All of this is handled by the database manager. So the first thing that the database manager might need to do is to check access control and make sure that any request that has been sent is a request that can be performed. So if you requested access to a particular type of data for reading, it has to check that you have been given read access to that data. If you want to delete it, then you need to have modified access to that data, etc. So you need to check, first of all, whether you are authorized to perform the operation that you are trying to perform as a user. Once that has happened, then control passes to the command processor, and that has to interact with the integrity checker, which has to make sure that what you're trying to execute does not break the integrity of the data. So you will have to check any constraints on the data, any business rules of the data, to make sure that you're not going to introduce inconsistent data, invalid data, etc. Once the integrity checker and the command processor have worked out whether this operation can proceed in terms of the integrity control, then the control passes to two modules, the transaction manager and the query optimizer, the scheduler. They are going to work together because each operation, as we will see, will have a series of transactions. And the DBMS will be executed concurrent transactions. So the scheduler has to schedule those concurrent transactions in a way that they have no ill effect for the users. So all of those pieces of software are interacting there to process the transactions that come, to make sure that they are executing concurrently, but without ill effect to the people that have, or to the users. So once there is a strategy decided by the query optimizer and the scheduler has a scheduler operations, then the next part of it is what we call the data manager. Is going to take care of the recovery mechanism, because every transaction that executes must be either executed completely or fully reversible. It has to leave the database in a consistent state. So the data manager which composes of the recovery manager and the buffer manager, has to make sure that the transactions execute fully to the point that the changes are made to the secondary storage, or they are rolled back so that the database is consistent to the point it was before the transaction started to execute. So it has the function of providing the recovery mechanisms for the whole database. And the buffer managers there are going to be the ones that are making sure that the transfer of the data is as efficient as possible from the point of view of transferring messages from transferring data from main memory to secondary storage backwards and forwards. Now, the last thing that we need to look at is how do we deploy databases, and if we look back to how they started to be deployed, the initial way of deploying databases was what they call teleprocessing, where you will have a single CPU, a very powerful CPU, and then dumb terminals that were connected to it. So the terminals weren't really doing anything, they were just displaying information. All of the work was being done by the single CPU. So all of the software was on this machine, and that was the application software, the DBMS software, etc. And the terminals were just displaying the information. These were the earlier systems. The problem, of course, is that in that particular model, the central computer is doing a lot of work, where the dumb terminals are not doing any work at all. So that is not going to be very good as an extensible architecture, because you are relying on one CPU doing all the work. So the next thing that happened was a file server architecture, where you have, we started to have the early local area networks, they moved to this type of architecture, where you have many workstations connected to a single central server. Now, in this case, the workstations are doing some work themselves. They are going to be, they have each of them a copy of the DBMS and the applications. So they are actually acting as reasonably powerful machines that are running the database management system, they are running the applications, and the server is just the file server. So the terminals are doing a lot of work, but when they send requests backwards and forwards, there is going to be a lot of traffic in the network, because they're not necessarily requesting a small bit of data, they are having to send lots of data as they process the data, because the DBMS is in the workstations, the database is in the other side, so they might have to request much more data than they need in order to perform an operation. So the traffic on the network is quite large. The control is also difficult, because instead of having one DBMS, each workstation is operating its own DBMS. So from the point of view of things like concurrency control, integrity control, and so on, it becomes quite a cumbersome system. So this wasn't exactly ideal either. And the next thing that occurred was what they call the client-server architectures. Now, in this type of architecture, which is the one that is the norm these days, we have workstations, which could be PCs, they could be Macs, they could be other type of workstations, connected to server computers. The application and the client software are on the clients, and the DBMS and database are on the server. So only the queries and the result of the queries are sent over the network. So that diminishes the network traffic. And also, it makes easier to control all of these issues of concurrency, integrity of the data, etc., because the server has the DBMS, so there is only now one DBMS running, so it becomes easier to handle all of these issues of integrity, etc. What has moved, the initial systems would have been done like that, but as we have moved into the world of the World Wide Web, etc., what we have found is that we have more than one layer of the client-server architecture. So what we have is a thin layer, which might be your web application, and then we have more tiers, and the web browser is the initial tier, and then you have more tiers that are behind to give you this end-client architecture. So you might have an application server and a database server. So instead of one layer, you have now more layers in this new architecture. And this is the architecture that has become the norm. So now we can go on to this and see how well this lecture has gone. So we can say a database schema is what? The content of the database, a collection of related data, a state of the database, or a description of the database using a specific data model. Who thinks is A, the content of the database? No. B, the collection of related data? No. C, the state of the database? No. D, yes, we all got it right. See, the ones that were left were the better ones. I'm glad. Right. So, which of the following is not a function of a conceptual database model? The conceptual database model is the middle layer. So, shows how the database will be implemented in a DBMS, acts as a communication tool between end users and designers, enables the database users to understand the structure of the database, or represents the relationships between the data. Which one is not a function of the conceptual DBMS? So who thinks is A? Shows how the data will be implemented on a DBMS. This is the conceptual model, which is the middle one. Okay. B, acts as a communication tool between end users and designers. C, enables the database users to understand the structure of the database. At least 1, 2, 3. Okay, we're gathering momentum. 4. D, represents the relationships between the data. Oh, so most of you are non-voting in this issue. Well, the right answer is A, because what we're trying to do is separate the implementation details from the conceptual model. So what it doesn't do is it shows you how it's going to be implemented, because we're trying to stay away from the implementation details when we are defining the conceptual model. And then one final one. This is true or false. The answer, this is less answers, so you have more chance of getting it right, which will make you leave in a good note, thinking you've understood everything about this. The ANSYS Spark 3-level architecture was proposed to address the issue of data independence. Is this true? Those that think it's true, raise your hands. Okay, those that think it's false, raise your hands. The truths have it. It was to do with data independence.